Hello. In this video we're going to continue with Lab 2, and I just wanted to go over a few of the measurements that need to be taken to characterize your op amp. So we're going to go over the input bias currents, input offset current, input offset voltage, and the slew rate. Okay, to measure the input bias current, you're going to want to disconnect the AC voltage source from the positive terminal and set the positive terminal to ground. So now you want to notice that the positive terminal is to ground and the negative terminal is also to ground. This negative terminal connects to the input resistor and the feedback resistor, which there is no AC source to. So you're going to run the sample, and to measure current at the base, you just take your cursor, it's going to turn into a probe, and then get closer to the transistor's base and it'll turn into a circle. Once it's a circle, you can measure current. So do that for both sides. And now we have 500 or 5.289 microamps for the positive terminal and 5.256 microamps for the negative terminal. So going into the lab manual, we can see now that we have those two values, you can just take the absolute value of the difference, and that'll give you your current offset. Now moving on to voltage offset. So your voltage offset is going to be very similar. You're going to make sure both inputs are set to ground, and we're going to measure the output, and theoretically the output should be 0, but what we're going to notice is that there's an DC offset at the output. Be aware that we do have a noise gain, so any type of voltage that's at the input is going to be amplified by our gain. So we're going to go ahead and run this and measure the output, and we can see we have negative 18.93 millivolts. And so negative 18.93 millivolts divided by our gain will give us our voltage offset. And just to see what that looks like, this is the 18 millivolts that we just measured. We have our gain, and we're trying to solve for our voltage offset at the input. So in the workbook activities, you've probably learned about the compensation resistor. So if we put a compensation resistor here, theoretically we should get even less of a offset voltage, and the compensating resistor should be the feedback resistor in parallel with the input resistor, so that should give us a value of 900. And we run this, and our value is actually worse. We have more DC offset at the output. And I believe that this is like a glitch in the software, and I want to show you a different way to measure offset, just to be able to make sure that your compensating resistor is doing its job. So what we did in the beginning is we set both inputs to ground and we measured the output, which theoretically should be 0. Well, if we send the same signal into both inputs of the op-amp, you're taking the difference of the two, so they should cancel out and you should also get 0. So let's go ahead and try to do that. So we're going to delete our ground from the positive and negative inputs, and set the same signal into both, and I'll do it without the compensating resistor to start out with. So I'll run the signal, and notice that the DC component that we were measuring when we had them both set to ground was negative 18.9 volts. And so that is right around where we're measuring for the starting point of our sinusoid. So now what I'm doing is I'm just measuring the sinusoid, which I'm getting 196.9 millivolts. So by putting this compensating resistor into the circuit, it should get rid of any excess noise. So this value should probably go down, and it does. It dropped by maybe 0.4 millivolts. And if we increase this value to a value that's past ideal, this value should increase. And it did. Okay, so we're able to determine that the compensating resistor does function properly. I think that there's just an issue with using a compensating resistor in the software to measure the DC component. So when you do this for your lab, don't use a compensating resistor, and set both inputs to ground, just like this. And you'll get a DC value. And then when you get the DC value, make sure you're considering the gain, because the input voltage is going to be this value divided by the gain. And to see the formula for that, this is the 18 millivolts, this is our gain, this is our voltage offset at the input that we're trying to solve for. So for my example, it would be approximately 1.89 millivolts. Okay, now to measure slew rate. So before we get too in-depth into slew rate, I wanted to show you actually, let's start with a different method. I want to show you a screenshot. So when I took this course, I built the circuit and measured it on an oscilloscope. And measuring slew rate on an oscilloscope is fairly simple. One trick that I've learned is you just set the time scale to 1 microsecond, and then you're going to increase the function generator until you just barely start to get uh, a triangle wave. Like you start seeing a little bit of linear distortion. And then once you see linear distortion like this, you're going to measure the value, the amplitude of the signal. So I'm measuring a peak-to-peak value, which is 1.1 volts, which means that I would be getting a slew rate of 0.55 volts per microsecond, because you're taking the amplitude, and what I'm measuring is a peak-to-peak value. So looking at the frequency, I had to increase the frequency all the way up to 500 kilohertz to obtain this. So going into our example, I wanted to also show you that this is crossover distortion, and it's being caused by our Class B output. So if you want to measure slew rate, you're going to need to develop a Class AB push-pull amplifier for your output stage. Otherwise, you're going to have a really difficult time measuring slew rate. So the Class AB amplifier, you're setting a DC bias point here of about 0.7 volts, just enough to turn the diode on for both of these transistors, and that will help the crossover distortion go away. And I wanted to show you that because this next slide, I don't show you the output stage, but I'm using a Class AB amplifier. So I want you to be able to look up how to make an AB amplifier on your own. There's a lot of different versions of it. But this is my attempt in LTspice to increase the frequency of the function generator. You can see it's 270 kilohertz. And when I increased it, I didn't see linear distortion. And I increased it all the way up to 5 megahertz, and I was not able to achieve linear distortion or a triangle wave. So what I would recommend doing is obtaining the 90% and 10% of the output. And so what I would show you is that the input is still 0.1 volts peak to peak. So what you can do is come up here and right click on your mouse, and then you can just multiply it by 10, and that's what your output should look like. And so when you increase the function generator or the signal, you'll see that the amplitude starts decreasing. So looking at what the output waveform should be, we're getting 2 volts peak to peak. So that means the output should be roughly, I believe, roughly 1.8. Yeah, because 2 volts, 10% of 2 volts is going to be 0.2, which you would take 2 minus 0.2 and you get 1.8, which this isn't exactly 1.8, but you get the picture. And you would also get 1.8 on the upper portion. And you could see that there's a little bit of a DC component to it, so the upper portion right here is a little over 1.8, so that's why I'm doing a little less than 1.8 on the lower portion. And so once you do that, you obtain this value, which we're going to call 1.75 volts. And it's 1.75 volts over 1.83 microseconds. And let me just go ahead and copy these and bring it to my Excel. I'll show you this in 1 second. We're going to do one more method. So 1.75 and 1.8326, and that is microseconds. And so what you're going to want to do is you're going to want to have microseconds on the denominator. So what you do is you take 1.75 divided by 1.83 microseconds, and you're going to multiply that by let's just multiply it by 1 microsecond. E to the negative 6. Nope, something happened. There we go. Okay, so we have, it's 0.953, so 0.95 volts per microsecond, which is, I feel like that's pretty close to being accurate, because the one that I obtained when I built it was 1.1 volt per microsecond. And we obtained 0.95 volts per microsecond. Okay, so there's another way to do this if you don't want to try increasing the frequency. I think increasing the frequency and measuring the slew rate experimentally is very easy when you can see the linear distortion. But since we don't actually see the triangle wave or linear distortion on the output, it gets a little tricky because you got to measure, you know, the 10%, 90% portion. So there's another way, and again, I'm using a class AB amplifier in my output, so I'm not showing you, but you use a pulse or a square wave. And so just change your function generator to a pulse, use 0.1 volt for your initial values, And you could plug in all of these same values and you'll get a similar result. 1 microsecond rise time, fall time, on time, and your period. And then you run it and you do that same multiply by 10 up here to make the input look like what the output would, so you have a good comparison. And then you measure the 10% and the 90%. And I already did it here, and I got 1.57 volts over 1.13 microseconds. So, oh, and let's see, I already plugged it in here. So I got 1.39 volts per microsecond. So you can see we're measuring the same exact circuit, like nothing changed. We used two different methods. I personally think that changing the frequency method was a little bit more accurate. I think it is much more accurate when you can see the linear distortion, like if you do it experimentally. But give the pulse wave a shot, and I would just choose one and document it, put it in your report, and compare it to a LM741. I hope this helps. Thank you.